In today's video, let's deep dive into Ito's calculus. For centuries, the physical sciences have relied on deterministic models to describe the world, from the orbits of planets to the flow of electricity. These models, covered by ordinary differential equations, operate on the principle that given a precise set of initial conditions, the future state of a system can be predicted with a certainty. However, when this paradigm is applied in financial markets, its limitation became starkly apparent. The intricate dance of asset prices is influenced by a myriad of unpredictable factors, geopolitical events, and shifts in investor sentiment and unexpected economic data. A simple model assuming constant growth, for instance, fails to capture the inherent uncertainty and volatility that drives the market. The recognition of this fundamental unpredictability led to the development of the random walk theory, a cornerstone of modern finance, which poses that successive changes in asset prices are independent of one another. This idea suggests that the future price movements cannot be reliably predicted from past movements alone, rendering the market a landscape of irreducible uncertainty. To navigate the landscape, a more sophisticated mathematical toolkit is required, a one that embraces its randomness rather than ignoring it. The mathematical framework for modeling systems that evolve randomly over time is a stochastic process. A stochastic process can be thought of as a collection of random variables indexed by time, providing a snapshot of the system state at any given moment. To describe the dynamics of these processes, especially in continuous time framework favored by financial theory, a specialized tool is needed. The stochastic differential equation. An SDE is analogous to an ordinary differential equation, but it includes an additional term to represent the source of noise or randomness. This structure allows SDEs to model the evolution of a variable as a combination of predictable deterministic trend and an unpredictable stochastic fluctuation. This dual nature makes them exceptionally well suited for describing the behavior of financial assets, which exhibits both long term and short term movements. Among many SDEs in finance, one that stands out for its historical importance and mathematical tractability is the geometric Brownian motion. GBM is the workhorse model for asset prices and is most famously employed as the underlying process in the Black-Scholes-Merton option model, a landmark achievement in financial economics. The GBM model is this. The GBM model is described by the following ST. DST is equals to mu into ST into DT plus sigma into ST into DWT. The equation elegantly captures two essential features of asset price dynamics. The first feature, mu into ST into dt, is a drift representing the deterministic trend or the expected rate of return of the asset over a small time interval dt. The second feature, sigma into ST into dwt, is a diffusion representing the random volatile component of the asset's movement. In this video, we'll perform a complete deconstruction and reconstruction of this pivotal model, starting from fundamental random concept and building the necessary mathematical machinery. The source of randomness in the GBM model, and indeed in vast number of STs, is a specific type of stochastic process known as the Wiener process, or the Brownian motion, named after the botanist Robert Brown, who observed the erratic movement of pollen particles suspended in water. Its mathematical formulation provides the fundamental building block for continuous time stochastic models. A standard Wiener process, denoted as WT, is formally defined by three core properties. The first property is that the process should start at zero, that is, W0 or W0 should be equal to zero. The second property is that for any sequence of times where 0 is less than or equal to S is less than T is less than U is less than V, the change in the process over the time interval ST, which is WT minus WS, is statistically independent of the change over the time interval UV, which is WV minus WU. This memoryless property aligns with the efficient market hypothesis, where past movements do not influence the future movements. The third property of a Wiener process is that the change in the process over any time interval of length T minus S, denoted by WT minus WS, follows a normal distribution with mean zero and variance T minus S. This property makes the Wiener process an ideal candidate for modeling the cumulative impact of countless small independent shocks that drive the asset prices in a financial market. A superficial glance at the properties of Brownian motion might suggest that it behaves like any other continuous function. However, its part exhibits a profound and counterintuitive characteristic. While it is continuous everywhere, it is differentiable nowhere. The path is infinitely rough, or fractal-like, meaning that no matter how closely one zooms in on one segment of the path, it never smooths out in a straight line. This lack of differentiability has monumental consequences and is the primary reason why the rules of ordinary calculus are insufficient for analyzing a stochastic process. The infinite roughness can be quantified by examining the path's variation. The total variation of a function over an interval measures the total distance it travels up and down. For any conventional smooth function, this value is finite. For a Brownian motion path, however, the total variation over any time interval is almost surely infinite. The path oscillates so violently that it covers an infinite vertical distance in a finite amount of time. This is where the concept of quadratic variation becomes essential. Instead of summing the absolute changes WTI minus WTI minus 1, quadratic variations involve summing the squared changes WTI minus WTI square over a partition of a time interval. Formally, the formula for variation over a time interval 0 to t is given as V sub t of x equals the supremum of over all partitions pi of sum I equals to 1 to n of the absolute value of xti minus xti minus 1. Here, supremum means that the least upper bound, but you can read it as the maximum taken over all possible ways to split up the interval. For each interval, calculate how much the function exchanges and add up all the changes within the partition. Finally, take the largest possible value this sum can achieve across all partitions. Formally, the quadratic variation of a process xt over the interval 0 to t is given as x sub t, or the quadratic variation of x over the time interval 0 to t equals the limit as the mesh size of partition pi approaches 0 of sum of square of xti minus xti minus 1. Here, the mesh is the size of the largest interval in one partition. Now, in plain English, we first chop the time intervals 0 to t into small pieces. For each piece, calculate how much the process xt changes and square the change. Add up all the squared changes. Refine your chopping until the pieces get arbitrarily small. That's quadratic variation. Here, as you can see in the series of equations, for a smooth deterministic function, the sum converges to 0. But for a standard binary process, the result is astonishingly different. The quadratic variation, Wt, over the interval 0 to t is exactly equal to t. This non-zero quadratic variation is the single most important property distinguishing stochastic calculus from classical calculus. It can be understood heuristically by considering a small time interval dt. From the properties of a process, the increment dwt is equals to wt plus dt minus wt is a random variable with mean 0 and variance dt. Since the mean is 0, the variance is equal to the expected value of the square of the variable. Therefore, var of dwt is equals to dt. In the limit of infinitesimal time steps, this execution becomes an equivalence leading to the most famous fundamental rule of Ito's calculus. Dwt square is equals to dt. This relationship reveals that the squared infinitesimal increment of a linear process, dwt square, does not vanish at, at a faster rate than dt. Instead, it is of the same order as dt. The entire machinery of Ito's calculus, particularly Ito's lemma, is built to correctly account for the mathematical consequences of this non-vanishing second-order behavior. It is not merely a notational convenience, but a necessary adaptation to the unique geometry of random paths, which are fundamentally different from the smooth curves of the deterministic world. The non-zero quadratic variation of Brownian motion directly leads to the breakdown of fundamental rules from ordinary calculus, most notably the chain rule. To illustrate this, consider a simple function, a Wiener process fwt is equals to wt square. A naive application of the classical chain rule will suggest that dwt square should be equal to 2wt dwt. However, this is incorrect. As demonstrated in the Ito's framework, the correct differential is dwt square is equals to 2wt dwt plus dt. The emergence of the additional dt term is direct consequence of the property dwt whole square is equals to dt. This discrepancy, this discrepancy underscores the need for a new, more robust version of the chain rule that is compatible with the unique nature of the stochastic process. This rule is known as Ito's lemma. The intuition behind Ito's lemma can be effectively conveyed through a heuristic derivation using a Taylor series expansion. Consider function f that depends on both a stochastic process xt and time t. We wish to find its differential df. Expanding f around the point xt, t gives df is equals to partial derivative of f with respect to t into dt plus partial derivative of f with respect to x into dxt plus half into second order partial derivative of f with respect to t square with respect to t into dt plus half into second order partial derivative of f with respect to x into dxt square plus second order partial derivative of f first with respect to x then with respect to t into dxt dt. Now let's assume xt is an ITOS process governed by this SDE. dxt is equals to mu dt plus sigma dwt. We substitute this into the Taylor's expansion. The crucial step is to evaluate the second order term dxt square. Dxt square, when expanded, can be written as mu square dt square plus 2 mu into sigma into dt into dwt plus sigma square into dwt square. To simplify this, we apply the multiplication rules of Ito's calculus, which are derived from the orders of magnitude of the infinitesimal terms. dt square tends to 0, as this term is of a higher order than dt and vanishes. dt dwt also tends to 0, as this cross product term also vanishes. Now, as we discussed earlier, dwt square tends to dt. This is the non-zero quadratic variation property. Applying these rules, we get dxt square is equals to sigma square dt. Now, substituting this back into the Taylor series and keeping only the terms of order dt or lower, we get df is equals to partial derivative of f with respect to t into dt plus partial derivative of f with respect to x into mu dt plus sigma dwt plus half into second order partial derivative of f with respect to x into sigma square dt. Collecting the dt and dwt terms yield the general form of Ito's lemma. This derivation shows that the extra term in the stochastic chain rule is not an arbitrary addition but emerges naturally from a standard Taylor expansion once the unique properties of a stochastic differentials are respected. The heuristic derivation leads to the formal statement of theorem. Let xt is equals to mu into xt comma t into dt plus sigma into xt comma t into dwt. If f is a function that is twice continuously differentiable with respect to x and once continuously differentiable with respect to t, then the process yt, which is equals to f, is also an Ito's process, and its differential dyt is given by dyt is equals to d of f is equals to open brackets and partial derivative of f with respect to t plus function mu xt comma t into partial derivative of f with respect to x plus half into function sigma xt comma t whole square into second order partial derivative of f with respect to x whole into dt plus function sigma xt comma t into partial derivative of f with respect to x into dwt. This formula is a cornerstone of stochastic calculus and serves as the bridge between the dynamics of an underlying stock process xt and a function of that process fxt, comma t. Now, the most significant and initially counterintuitive part of Ito's lemma is the second order term, 1 by 2 into sigma square into second order partial derivative of f with respect to x dt. This term, which has no counterpart in the classical chain rule, represents a deterministic drift component that arises purely from the volatility of the underlying process. Its existence is a direct consequence of the non-zero quadratic variation dwt square is equals to dt. This term can be interpreted as the convex correction of the function. The choice to use Ito's calculus with its streamingly changed extra term is not arbitrary. Alternative formulations of stochastic calculus exist, where the familiar classical chain rule holds. The preference for the Ito's formulation in finance is deeply rooted in the economic theory. A key property of Ito's integral is that it is a martingale, meaning the expected future value of the integral given all the information up to the present is simply its current value. In financial terms, a martingale represents a fair game where no predictable profit can be made from the past information. This aligns perfectly with the principle of no arbitrage, which is the fundamental assumption in asset pricing. The ITOS framework ensures that the random component of an asset's price movement cannot be exploited by a trading strategy to generate risk-free profits. Therefore, the additional term in the ITOS lemma is the mathematical price paid for a framework that is consistent with the core economic principle of an efficient market. With the machinery of ITOS calculus established, it is now possible to fully analyze the geometric Brownian motion. The SD for an asset price ST following GBM is formally written with previously as we previously discussed, the ST for an asset price ST following a GBM is formally written as DST is equals to mu into ST into DT plus sigma into ST into DWT. The drift term mu into ST into DT is a deterministic part of the price change. It states that over an infinitesimal time dt, the asset price is expected to grow by a certain percentage UDT. The change is proportional to the current price ST. The diffusion term sigma STDWD is the stochastic or the random part of the price change. It models the unpredictable fluctuations around a drift. The magnitude of this random shock is also proportional to the current price ST, meaning the model assumes constant percentage volatility. The term DWD represents the increment of a binary process, acting as a source of randomness. The drift term U is the annualized expected rate of return, and the volatility term sigma is the parameter representing the annualized standard deviation of the asset's return. Now, the strength of GBM is that it is non-negative. The model ensures that the asset price ST can never be negative, and the model implies log normal returns, which means that percentage returns are independent of the asset's price level, which is a reasonable approximation of reality. The next is that the paths generated by GBM exhibit a continuous but jagged character that visually resemble a real-world asset price charts. Also, GBM shows mathematical tractability. The GBM SDE has analytically closed form solution, which makes it extremely convenient for applications like option pricing and simulation. The limitations of GBM is that it is modeled on constant volatility. Real world market volatility is known to be varying and often stochastic. The next limitation is that GBM generates continuous price paths, meaning it cannot account for sudden discontinuous jumps in the asset prices that can be caused by major unexpected news such as earning surprises and much more shocks. Next limitation is that the model assumes that logarithmic returns are normally distributed. Empirical studies of financial returns have consistently shown that they exhibit fat tails, meaning the extreme events occur more frequently than a normal distribution would predict. Now, let's look into deriving an analytical solution for GBM. The derivation proceeds as a direct application of Ito's lemma. This is a meticulous step-by-step process that reveals the origin of every term in the final solution. First, we create a new function where let the function fst is equals to ln of st. We need to find its partial derivatives with respect to st and t. Partial derivative of f with respect to st is equals to 1 by st. Second order partial derivative of f with respect to st is equals to minus 1 by st square, and the partial derivative of f with respect to t is equals to 0, since f does not explicitly depend on t. Now, from the GBM SDE, we have to identify the drift and diffusion coefficients. The drift coefficient mu of st comma t is equals to mu into st, and the diffusion coefficient is sigma into st. Now we know the Ito's formula for df st comma t. Now substituting all the results we got into this equation until now, we get d of ln of st is equals to 0 plus ust into 1 by st plus half into sigma st square into minus 1 by st square whole into dt plus sigma st into 1 by st dwt. Now, simplifying this expression where the terms cancel out neatly, we get d of ln st is equals to mu minus 1 by 2 sigma square whole into dt plus sigma dwt. Now that we have the simplified SDE with constant coefficients, we can integrate it directly from time 0 to time t. Integrating this function from 0 to t limits, we get ln of st minus ln of s naught or ln of s0 is equals to mu minus 1 by 2 sigma square t plus sigma wt. This can be written as st is equals to s naught into exponential function of u minus 1 by 2 sigma square whole into t plus sigma wt. The significance of the term minus half sigma square, often called the Ito's correction or drift adjustment, is a crucial component of the solution. It adjusts the arithmetic rate of return mu to a geometric rate of return suitable for continuously compounding process. Its significance goes beyond a mere mathematical artifact. It reveals a profound statistical property of asset prices under JBM. Now, let's examine the expected mean value and the median value of the future price ST. The expected value is given by E is equals to S naught into e to the power of mu t. Notice that the expected price grows at the rate of mu, the arithmetic mean of return, and is independent of volatility. Median is given by S naught into exponential function of u minus 1 by 2 sigma square whole into t. The minus half sigma square term explicitly lowers the growth rate of the median price related to the mean price. This means that for any non-zero volatility, the average outcome of many simulations will be higher than typical or most probable outcome. A naive simulation that omits this correction would correctly model the average price but would systematically overestimate the median price, potentially leading to a flawed risk assessment and overly optimistic performance forecasts. The Ito's correction ensures that The model for the most probable path is correctly centered, providing a more realistic picture of the likely evolution of the asset price. Now let's look at a practical walkthrough. We are going to be doing a Monte Carlo simulation of GBM in Python. Monte Carlo simulation is a powerful numerical technique for exploring the behavior of stochastic processes. It involves generating a large number of future paths of the process to understand the distribution of potential outcomes. To implement this on a computer, we must first convert the continuous time model into a discrete time approximation. For many STs that lack an analytical solution, this requires using an approximation scheme, which introduces a discretization error. However, because we have derived the exact analytical solution for GBM, we can create an exact discretization scheme that has no approximation error. The solution ST is equals to S naught, and the exponential function of the terms describes the price at any time t relative to the price at time 0. This relationship holds between any 2 points in time. We can write the price at time t plus 1 in terms of the price at time ti using the same solution. So sti plus 1 will be equal to sti into exponential function of u minus 1 by 2 sigma square into ti plus 1 minus ti plus sigma into wti plus 1 minus wti. To create a formula for numerical simulation, we replace the continuous variables with discrete counterparts over a small time step delta t, which is equal to ti plus 1 minus ti. The Brownian motion increment wti plus 1 minus wti is a normally distributed random variable with mean 0 and variance delta t. We can therefore represent it as root delta t into z of I plus 1, where z of I plus 1 is a random draw from a standard normal distribution n is equal to n of 0, comma 1. This substitution gives us the final iterative formula for the Monte Carlo simulation of GBM. So S of I plus 1 is equals to Si into exponential function of mu into minus 1 by 2 sigma square into delta t plus sigma into root over of delta t into zi plus 1. By applying this formula repeatedly, we can generate a complete price path from initial value S0 to a final time ST. Now, for the simulation we discussed, let us look at the parameter set. We will take S0 as 100, the annualized drift or expected return as 8%, the annualized volatility as 20%, the time horizon in years as 1 year, the number of time steps as 252 trading days, and number of simulation paths or trails as 10,000, and delta t will be 1 by 252. The following Python code implements the Monte Carlo simulation for the geometric Brownian motion using the parameters defined before. The code leverages the NumPy library for efficient numerical computations and matplotlib for visualization. This code is heavily commented, so just by reading the comments, we can understand the code easily, and the link to this code is added in the description. So the simulate GBM function simulates the geometric Brownian motion paths using the exact discretization method we discussed. It first calculates all the parameters needed, such as dt, z, drift term, and diffusion terms, then combines drift and diffusion to get the log returns for each step, then finds the cumulative log returns. Now, it calculates the price paths and sets the initial price for all paths, and calculates the rest of the path using the exponentiated cumulative log return, which is equal to st is equals to s naught into exponential function of cumulative log returns. Now, the last step is to create a time array for plotting, and this function returns the variables paths and the time points. Now, in main, we define the simulation parameters which we discussed earlier, which is S naught is equals to 100, the annualized drift is equals to 8%, the volatility is 20%, the time horizon is 1 year, and the time steps is 250, and the number of simulation paths is equals to 10,000. Then we run the simulation and store the price paths and time points. Now, we plot the figures and calculate and display the theoretical and simulated statistics. The output of the Python script provides two key visualizations to confirm the theoretical properties of geometric Brownian motion. First, the plot of the first 50 simulated paths shows a fan of possible trajectories for the asset price. All paths originate from the same starting point S0, which is equals to 100, and then diverge over time as random shocks accumulate. This visualization powerfully illustrates the concept of risk and uncertainty. While the general trend is upward due to the positive drift of 8%, the range of possible outcomes widens significantly as the time horizon increases. The second histogram of the final asset prices after 1 year displays the probability distribution of the terminal price ST. The shape of the histogram is distinctly not a symmetric bell curve. Instead, it is right-skewed with a wrong tail to the right, which is characteristic shape of a log normal distribution. This is a direct visual confirmation of the analytical solution, which involves an exponential function of a normally distributed random variable. The plot also validates the crucial distinction between the mean and the median. As predicted by the theory, the mean of the distribution is noticeably higher than the median. The close agreement between the simulated statistics and the theoretical counterparts serves as a robust validation of the simulation's correctness. This confirms that the ITO's correction term minus 1 by 2 into sigma square accurately models the wedge that volatility creates between the average outcome and the most probable outcome. Today, we have navigated the path from the abstract principles of stochastic calculus to the tangible application of simulating asset prices. The journey began by establishing the necessity of stochastic models to capture the inherent randomness of financial markets. We then deconstructed the engine of this randomness, the Wiener process, focusing on its most critical and counterintuitive property, the non-zero quadratic variation. This property was shown to be fundamental reason why classical calculus fails and why a new framework, Ito's calculus, is required. The cornerstone of this framework, Ito's lemma, was derived and explained as the stochastic equivalent of the claim rule. Its application was demonstrated by using the stochastic differential equation for geometric Brownian motion, the canonical model for asset prices. This derivation revealed the crucial role of the volatility-induced drift adjustment, clarifying its statistical interpretation as the difference between the mean and the median of the resulting log normal distribution. Finally, this entire theoretical foundation was brought to life through a practical Monte Carlo simulation in Python, providing a robust error-free method for generating and analyzing potential asset price trajectories. While geometric Brownian motion is an indispensable tool for both education and basic financial modeling, its limitations, namely constant volatility, continuous paths, and normally distributed log returns, necessitate the use of more sophisticated models for many real-world applications. The foundation built today serves as a gateway to understanding these advanced models, which often extend GBM framework to address its shortcomings. By mastering the principles of Ito's lemma and the simulation of geometric Brownian motion, one is well equipped to explore the richer and more complex landscape of quantitative finance, building models that more closely reflect the intricate dynamics of the world's financial markets. Thank you.